Okay, welcome. Sean Maroney here. We're in Physics 105P, and we're going to do our second lecture. And it's going to complete Chapter 9 in our textbook. So let's just go straight to the screen. I should say, a couple of intro pieces of information. We're going to cover here sections 9.3, 9.4, 9.5, and 9.6. And some of these are very short sections. There's going to be problems with them. There's going to be homeworks associated. And the second test will focus on these sections. Section 9.7 is about pulleys. We're not going to cover that in this course. It's easy to read though, so you can check up on that. So let's go straight away and talk about the topics that are in there. And we're going to share the screen. And I've pulled up a PowerPoint and I've got a whiteboard. So hopefully this will work better than recording one. Here is our bridge. Here's our textbook, Chapter 9, Rotational Motion. And let's get the slideshow going. And we'll be cutting back and forth between the whiteboard and the PowerPoint. So there's our bridge. It's on the cover. We don't know quite where that is. Portugal has a bridge like this, but I think Florida does too. So we're going to talk about centripetal force. And there's that word in parentheses toward the bottom, centripetal force. And what we're seeing here is you got a rock tied with some kind of cord, and it's being spun around. So you've done this sort of thing. You get a ball or whatever, and you spin it, hold it up over your head, you spin it in a horizontal plane. Let's think of this as the horizontal plane, and we are looking down on it. And we know that the rock is not going to follow a straight line path. It's going to follow a curved path, more or less like a circle. And it's going to come around, and it's going to come back to where it started, sort of an orbit. And you could do this vertically as well, but then you got to deal with gravity. So by looking at this as horizontal, we're not going to deal with the gravity. So the path that at this instant of time that we're looking at it, the rock is located right there, and the green arrow represents the force exerted by the string, because that rock is not going to follow a curved path unless a force is exerted upon it. Newton's first law says that something is going to continue in a state of uniform motion, which means the same speed and the same direction, unless it's acted upon by an outside force. And we have looked at forces that are aligned with the motion, but here we have a force that's perpendicular to the motion, and that produces a completely different result. It deflects the rock over to, as we're looking at it, down the screen, the rock will be moving. And the direction the rock would go, due to its inertia, according to Newton's first law, is straight to the left. If that string weren't there, and we'll see that in the next picture, but this is what we've got, and this we call centripetal force, not to be confused with centrifugal force. And people will pronounce centrifugal as centrifugal, which sounds a lot like centripetal. And people get confused. What are you talking about? What kind of force you're talking about? Centrifugal force would have to be in the opposite direction. Centri means to the center. Petal is from a Latin word meaning seek. And just like the word petition, you're seeking something with a petition. And this is the root, P-E-T. And so this rock is seeking the center. This force is seeking to bring the rock to the center. But the rock might, what if the rock were to go away from the center? We'd say it's fleeing the center. So you think of fugitive, and that's where you get centrifugal force. So when I talk about centrifugal force, I will emphasize it by saying centrifugal, so as not to confuse it with centripetal. But I don't think we're going to see much of centrifugal force here at all. And this is our brief introduction to centripetal force. On our next slide, we see what happens when the rock is traveling, and what if that string breaks? Then suddenly the force vanishes. It's not there anymore. And the rock has zero net force on it. And we're not counting gravity. So we're looking down horizontally. Now the rock is not going to follow the curved path because the force has vanished. There is no centripetal force anymore. The rock will, from the instant that the force has gone to zero, the rock will proceed in a straight line at a constant speed. And we see that where it's going out to its green shadow. Okay, I want to switch out now to, let's see how this is going to work. I got to end the show right here. And I want to stop sharing that. And I want to share the screen with the whiteboard. And what I want to put up here on the whiteboard is our formula for centripetal force, the one and only formula we'll have here. Let's just make sure, good, I've got a wide one. Let's have a nice blue color. And the force is going to depend on three things. So F is going to equal mv squared. That should look a little familiar from kinetic energy, but this has nothing to do with kinetic energy, divided by r. So three factors come into play with centripetal force. How much mass do you have? How much mass does that rock have? How fast is it going? That's v. And this is speed. We don't care about direction at all with this. And r is the size of the circle, the arc that it's following. So there's four things here, and if you know three of them, you can figure out what the fourth one is. And so let's look at, in our textbook, we have examples to illustrate these points. So I am going in our textbook to page, it's page 233, 233. We have example 1. Oh, there's one thing we got to remember here. Well, no, that's the wrong section. We did that last time. Let's go to section 9.3. Okay, 9.3. So the page we want to be on is page 243. Oh, and I should have stayed with the slides. So let's just hop back out and let's look at a slide to illustrate this particular problem. So we're there. Let's see, we need the slideshow on. And there it is. There's from our textbook on page 243. We have this car. It's on a curved road path. It's moving at 15 meters per second. We see the radius is 25 meters. We recognize 3 sig digs for this one. And that's going to be how we handle the problem. And the problem tells us, gives us information. So we have some data. Let's go back to the whiteboard so we can properly set this problem up. So end the show and stop the share and then start the share and go to the whiteboard. And the whiteboard preserves what we were doing last time. So we've got our formula. Now let's make a note over here. We're going to put our data. Collect all your data in one place so that you may properly organize it. And what have we got? An automobile of 1,640 kilograms. That's not weight, that's mass. So G is not involved here. We got a horizontal problem. We don't have to worry about G. So 1,640 kilograms. So we got that. Rounds a curve of radius 25 meters. We always want radius, we never want diameter. So if you see the word diameter, divide by 2 and you've got the radius. But here's the radius, 25.0 meters, I think. I lost my pen somehow again. So we learned last time, if I stop the share and start the share, puts us right back. And we have a pen. So 25, I should have put 0.0 meters. I'm not going to erase that because I'll lose the pen again. And what else do we have? With a velocity of 15 meters per second. So 15.0. How does this happen? We'll never get through this if we're going to have to do this all the time. Okay, so 15.0 meters per second. And so things we look at right away, do we have everything? No, just one more thing. It says, what's the centripetal force? So I got to calculate F. And F is going to equal question mark. And I recognize I've got 4 things here, and they're the same 4 that are in the formula up above, so I'm good to go with that. I look at my units. I got kilograms, meters, and seconds. That's the proper units to be having. And the combination of those should give us newtons. So we can make that assumption. I notice that there's 3 sig digs. So let's record that so that when we get to our answer, this is a reminder. And by the way, on the last test for week 3, I found that the people who are scoring and getting all the problems right were using the system I prescribed. And the people who didn't use that system, they tended more often than not to get the problems wrong. So there will be a new rubric coming out for week 4, and that'll be posted in Laulima. Meanwhile, we don't need that right now. So the calculations start by writing the formula down that you're going to use. And there it is. It's already written for me. And now, what's the centripetal force? Let's plug numbers in. So F is going to equal, and I won't write the units because I know they're correct, and I know that I'm going to be getting newtons at the end. So I've got 1640. Okay, multiplied by phi squared, so that's 15 squared. And we write down these things, and 25 is the meters. And we know this is going to be newtons, and so we do the multiplication. And we end up with 14,800 newtons, which has a 3 sig dig answer. And this is rounded off a little bit. And that's the force. And if you divide by 4, you're approximating roughly 4 newtons to the pound. So divide by 4, you're down around, I don't know, 3,700 pounds of force required to keep that car on the road. And remembering back to the picture, where is that force being applied? Is it being applied to the roof of the car, to the side of the car, onto the wheels? No, it's being applied at the roadway where the rubber and the concrete are in contact. And basically, it's a friction force. If that was an icy road, the car would not make a curve at all. It would go in a straight line. It would hit that railing and it would flip over and fall into the water. It's a very low railing. Okay, so you might want to ask, and this is not part of the problem, but what is the coefficient of friction of that roadway? So we're going to have to remember that the friction force, remember it was little f, is equal to a coefficient number times the normal force. And the normal force here is equal to the weight, and the weight is equal to mg. So if we had this as a part of the problem, we'd have to include g in our data because we're going to use that. And g, remember, is taken to be an exact value, and we have agreed that we're going to use 9.80. That's g. And that's going to be meters per second squared. Okay, so I could calculate mu if I knew the friction force, and I do know the friction force. The friction force is 14,800. That's what the road has to supply to keep the car on the road. And I have to figure out what is the normal force. So without writing down the numbers, because I've got them here and we've got a lot to cover, I want to put down that the weight is 16,072 newtons. Now, we don't round this off at this point because we're in the middle of a problem. So we're going to divide 14,800 for week 5. I need a graphics tablet. I'm not going to get one in time for this week. So 16,072. Okay, and I can see that it's a number that's less than 1, but it's up pretty close. And I worked this one out already, so it's 0.921. And that's up in the range of rubber and concrete. Okay, so now you need 14,800 to stay on the road, and friction is given it to you because you've got enough of a coefficient to do that. But what if it's a wet day, or what if it's snowy and the coefficient goes down to, let's say, 0.3? What's going to happen? If the coefficient goes down to 0.3, then the weight's not changing, but the friction force is less. And the maximum friction force you're going to get is not going to be equal to 14,800. It'll be less than that. And if you don't have enough force, the car is not going to follow that curve. The car is going to drift in a straight line and hit the guardrail. So what's your, as a good driver, what is your strategy going to be? You got to make that centripetal force less. You can't change the roadway with the R, you can't change the car's mass, but you have control over the speed. So you'll go at a slower speed. And we could calculate that, but we're not going to. But intuitively, you would know what to do driving. So this would be, and let's see, we had to box our answer. They asked us for this value, and so that's our answer. The rest was just something else I threw in. Okay, so that was example 1. Now, there's another example, I think, to look at, or is there? No, there is not. Okay, so that's as much as we're going to talk about on centripetal force. So our next excursion here is going to be to talk about power in rotational systems. And we have some examples to look at there. So let's clear the screen. No, let's not. Let's go to a fresh new page. Power. You remember from some time back, power is equal to work. Let's spell that out, because W is weight sometimes, and not the case here. Work divided by time. And work is measured in joules, or work is measured in foot-pounds, depending on the system you're in. And how did we calculate work? You're applying a force, and something is moving through a distance. So we have F for force, and D for distance. And so let's just look at D over T. What is distance divided by time? It should be velocity. So you could say that if you've got a force and something's moving at a velocity, and that velocity we're going to have to say is a constant velocity. If your velocity is changing, you need more advanced mathematics to handle it. So force times velocity. Now we're talking rotational systems. So rotational systems, it's the same idea. Power is going to be work divided by time. And back in linear stuff, we had a force and a distance. So let's just skip that because this repeats. Maybe I'll put ditto marks. And the analog to force is going to be torque. We use the Greek letter tau for torque. And displacement, it's a distance in a direction, but we're going to be talking about in angles. We have an angular displacement, so we're going to say a certain amount of angle. And this could be measured in revolutions, it could be measured in radians, it could be measured in degrees. and you're going to divide by time. Okay, so far so good. And now let's look at the theta divided by t. The angle divided by time, how much angle are you covering in a unit of time? That's a velocity. It's an angular velocity. And so we're going to have the torque. And the symbol for angular velocity looks like a W, but it's a Greek letter, omega, lowercase omega. And we write it like that. So tau times omega, torque times angular velocity, gives us the power. And that's the main formula we want to use. So now let's look at an example to see how are we going to do that. Example 1 on page 246 is asking us, oh yeah, units. Let's mention units first. We have joules per second in both of these, because work is joules, but we learned last time that joules per second has a name, and we call that the watt. And if you have 1,000 watts, we call that a kilowatt. Kilo is 1,000, like in kilometer. Okay, so let's just separate those. Now, example 1, page 246. How many watts of power are developed by a mechanic tightening bolts? So we need some data for this problem. So tightening bolts using 50.0 Newton meters of torque. So we're given the torque. It's a metric problem. Tell that from the units, newtons and meters. That's basic stuff. So 50.0 Nm for Newton meters. Now, joule is a force times distance. It's also a Newton times a meter. So torque and work kind of share the same unit, but we try not to, we don't call this joules. That would not be right, because we're not talking energy here. At a rate of 2.5 radians per second. So omega is going to be 2.50 radians per second. So we've got our angular velocity. And what else do we have? We have a question. How many watts of power? So power we have to calculate. Well, we got the formula right up there. Torque times angular velocity. We just have to make sure the units are going to be okay. And it's all metric. Radian is one of those. It's a very curious unit. It'll vanish and get out of your way when you start doing a problem. So power is going to be torque. We write this. One other thing to write, I see 3 sig digs. Let's get that down so we glance at that when we get a result, and then we know what to do. So we got that. Power is torque times omega. So we write the formula. And then we can just extend it with equals and start plugging numbers in. And it's going to be 50 times 2.5. And the units are going to come out okay. It's going to be Newton meters, let's put them in, per second. And radians goes away. And Newton meters is a joule. And joule per second is going to be a watt. And we multiply these, and this comes out to be 125, pretty much exactly. And we're going to say watts. And there's our answer. So the power is equal to that. But there's another thing on the question is how many kilowatts do we have? So to get the kilowatts, you need to multiply or divide by 1,000. In this case, if the watts are going to build up to be kilowatts, the number has to shrink. So I got to move that decimal point 3 places, and I'm going to have 0.125. And that 0 is important to put in there because it tells you there's a decimal point following, and it's not just a scratch of paper of ink on a page. And so we write kilowatts, and this is the second part of the same problem. And that was example 1. And then we have, I think we are also going to look at a couple more of these. Example 2 on the following page, 247. We've got an electric motor. Okay, so let's leave that there and we can come back to it. Example 2. We can hop around among these pages. It's a nice feature of Zoom. Example 2. What power in foot-pounds per second is developed by an electric motor with torque 5.70 pound-feet So what's with the pound-feet as opposed to the foot-pound? Well, torque and work are pretty much the same unit, but they're very different things. So foot-pounds is usually considered to be the energy unit of work, and so they make pound-foot be the energy, or it's going to be the torque unit. But it doesn't matter very much at all what order you're putting them in, and but we'll do that. And then omega is given to us as 425 RPM. Well, there we are. We got RPM now. And that is an angular velocity. It's revolutions per minute. Let's remember, we got these angle things. We did this last time. 1 rev was 2 radians. 2 pi radians, I mean. So that's about 6.28 radians for 1 revolution around a circle, which means the radian angle is that big angle we saw of 57.3 degrees. And this is the same thing as 360 degrees. We're not going to see much in the way of degrees as we do these problems. Okay, so we might come back to this. So what we got to do, we got to calculate, we want to find out what is the power. It's the big question here. And I do a quick scan of my numbers, and I see that I've got 3 sig digs, so let's make a note of that. And my units are the US units. I've got pounds and feet, but I have minutes. So this is going to be, let's expand that. It's 425 revolutions per minute. So you're going to have rev per minute. Okay, so power is going to be the torque times that. So we're going to have to convert the rev into radians and the minutes into seconds. So there's a little bit more in this process than met the eye. So let's start with P is going to equal, and all my units are okay, so I'll tack them on at the end. It's going to be foot-pounds per second. So 5.7 times 425 and I'm going to have to write the units here because we got to do a little converting. So it's rev per minute and conversion factors come as fractions. And so I've got rev, I don't want rev, I want to get rid of rev. So I put that on the bottom so it cancels. And I want radians. And my conversion right above tells me that 2 pi of these, 1 of those, makes it, and that takes care of the rev. Now I got to do minutes. Minutes is on the bottom. I want to cancel it out, so I got to put minutes on the top. And I want to bring in seconds to take its place. That goes on the bottom, and I know that 60 of those is equal to one of those. And at the end of the line here, I'm going to have foot-pounds. And that's an energy. I've just switched them around because we're heading for power, which involves energy. Okay, so one of the things the book shows us is that for computing this, if you're given a problem that has torque in this form, pound-feet, and you have RPM, you can simplify this. You don't have to be doing all these conversions because there's a formula that has the conversions built in. We know that revs are going to cancel. We know that minutes are going to cancel. And what we're going to have left is radians per second. So I got foot-pounds. That's not affected. And I've got radians per second. And radians is a very cooperative unit. It just goes away. We have foot-pounds per second, which is a power unit. Now, what they do in the book is they say, well, these two parentheses, you got 2 pi times 1 over 1 times 60. That is 2 pi over 60. That's the number you've got here. 2 pi over 60. And that number is 0.105. So they give us a formula there, and it's on the bottom of page 246. And this is pretty handy. Saves you having to go through a double conversion. It's already done for you, and here's this number. Throw that into the mix, and you compute. You get your answer, and with correct rounding, you get 254 foot-pounds per second. Okay, and that's example 2. Okay, now let's look at example 3. This is asking what horsepower is developed in a racing engine with torque 545 pound-feet at 6,500 RPM. Okay, so my data, the torque is given as 545 pound-feet. And the angular velocity is given as 6,500 RPM. And the 6,500 has a bar here, so we know right away 3 sig digs. And we're after power. We want it in horsepower, but we're not going to get that on the first step. We're going to get foot-pounds per second. And let's see, this is RPM. Well, this is this problem lets us use that formula we just had. I'm going to use the 0.105. So power is what we're after. And the formula I'm going to use is power is equal to the torque times the omega. And this is the RPM omega, not the radians per second omega. Never mix those two together, times 0.105. 0.105. There. Okay, let's throw our numbers in. So I got 545. times, and then I got that 6,500. That's not a subtraction sign. That's not a plus sign either. It's a multiply sign. So just remember that. 6,500 times the 0.105. And that's going to come out as foot-pounds per second, and we will get, what will we get? Find that problem. We are getting, and I'm on the way to the answer, but I'm not at the answer, so I'm not going to round this off. I'm getting 371, 962.5, and that's ripe for rounding, but we're not there. Okay, and it's foot-pounds per second. Okay, now to convert that, I have a conversion, and that is that 1 horsepower, this is defined, and I don't know where the definition came from, but goes back to the days when horses did all the work before the internal combustion engine came along. 550 foot-pounds per second. So if I've got 371 odd thousands of foot-pounds per second down there, I'm going to have to divide by 550. So let's just make a note here. This is the power in horsepowers. So we're going to take this number, which should be on your calculator screen, because you haven't rounded stuff off yet. You never round off till the very end of a problem. Otherwise, you throw errors into it, but people do that. Even textbooks do that. So we're going to divide by 550. And when we get that number, then we do 3 sig gigs. And we have horsepower. So this is going to come out to be 676 horsepower. So that would be the power of that particular engine. Okay, now, is there any more to do on this? I don't think so. I think we come to, we might do one problem out of the problem section on page 248. Because it's always good to practice on these things. So this is 9.4. That's a 9.4. And we're doing number 17. And let's read the problem. A tangential force of 150 newtons. Okay, we're gonna have to draw a picture here. Let's get started. Data section. 150 newtons is a force. That's not a decimal point. Let's make that part of the 5. So I got 150 newtons applied to a flywheel of diameter 45 centimeters. Right away, 2 things I don't like. Diameter, I want radius. Centimeters is not a proper unit. Meters is the only proper unit. So we're going to have to change that. First of all, you want the radius. So you're going to divide by 2. So that's 22.5 when you divide it. And then you want to make the centimeters grow to be meters. The number has to shrink. It's 2 decimal places. So it's going to be 0.225 meters. And that's what we want. And we don't want this. Let's put a line through it. So we ignore it. We've got newtons and meters. That looks good so far. It's a tangential force. Let's draw a picture. So here's a flywheel. It's a circular thing. That's a circle. And here's a force being applied here. This is F. It's tangential. So it's going to make this thing spin. And what else have we got? What's it telling us? To maintain a constant angular velocity of 175 RPM. If you have a force, you're going to produce acceleration. If you're going to get a constant velocity of any type out of it, there must be an equal and opposite force, so you have a net of 0. So there's probably friction in the flywheel mechanism. We're not concerned about the details of that. We're just going to say this is constant. And it's RPM. So are we going to use the 0.105? Maybe. Let's see where this is going. Where is this going? How much work is done every minute, per minute? Well, we already got minutes built in here. Work is force times distance, and we got the force. So the question is, how much distance are we talking about? We're talking about a circle, and circles have a distance around the outside called the circumference, and that's 2 pi r, and that's one revolution will give you 2 pi r of distance. And if you've got, you're doing 175 RPM, every minute you're going to get 175 of those. So your distance is going to have to be 175 times the single circumference of 2 pi r. And here I'm using d for distance. I had d for diameter over there, so don't get confused on that. That's a different thing. 2 pi r. All right, so my distance, well, that's my distance. Let's set up the work. Let's just combine it all together. So the work is going to be the force. This is going to be meters, the distance, and the force, we already know it's newtons. So we're going to get joules. So I'm not going to bother writing the units. 175, I'm writing the distance first. Okay, I'll do that in reverse order. Times 2 times pi times 0.225. And then I didn't write down the force first, so I'll write down the force last. It's 150. And if you're multiplying, it doesn't matter what order you do it in. Okay, so yeah, I'm not going to use the 0.105 because we're not dividing by 60. So I've got 1, 2, 3, 4, 5 things to multiply, and I'm going to get, what kind of units am I going to get? I'm going to get, I guess, watts. The work is, oh, this is work. This is the work that's done every minute. So this has to come out to be joules. It's newtons times meters. And let's see, when we multiply these numbers out, and then we apply our 3 sig digs, which we should have written down. And then we're going to get 676 horsepower. Because they asked us for what's the work in horsepower. And so we box it, and we got our answer. Okay, so that's the first diagram we've had to do. Okay, now we're going to switch gears, literally, and start talking about gears. We want to talk about rotational motion and how you transfer it in a machine. So I think we got to go back to the slides, and let's pull them in, and there they are. So let's move on. Let's get the show going, and let's move on from here. Okay, so I think we did this problem. That was example 1, and we did this problem, and we did this problem in horsepower. I think then we threw in something else. Okay, these are 2 drums, and it's a small one and a big one, and they're attached, they're part of a machine, and the one on top is moving, it's rotating, and it's causing the one below it to rotate. So there's good friction between them, there's no slippage. And so it looks like roughly we could say that the one on top has half the diameter of the one on the bottom. The one on the top is rotating, and there's a one-to-one match of the surface. There's no slippage. Whatever the distance circumference of the upper one is, it is half the circumference of the one below. The one below has double the circumference of the one above. So it sort of stands to reason that if the one above is going to rotate 2 times, it will cause the one below to rotate 1 time, because you have to have an equal match of the distance around. A system like this, it's okay for certain purposes, but for operating a lot of machinery, this is not okay, because slippage is going to come in, moisture can seep into all sorts of places, and then the friction changes, and then your mechanism doesn't work the way it's advertised. Better is gears. Gears have teeth, and the teeth interlock, and there's no slippage possible here. One gear tooth, one tooth is from the upper is going to push on one tooth from the bottom. So there's an exact one-to-one correspondence. If you have, let's say, 15 teeth on the upper gear, you're going to have 30 teeth on the lower gear if you still have that 2-to-1 ratio between these. And so you're not going to get slippage with that. And we'll be talking about how many teeth gears have. And pulleys can be made to work the same way. But again, now you have, the wheels are not in contact except via a belt. And we have to assume that that belt has high friction so that it's not going to slip. If the belt slips, you know that you're not going to transfer that motion. And if that's your car engine, well, you need a new belt or something. Belts wear out. Okay, so we're going to be talking about gears. But I should go back and talk about the important equation from number 9.5. So let's hop back to the whiteboard and let's get a fresh page. And now we're talking about drivers and driven. When we looked at the drums, we looked at the gears, we looked at the pulley in those 3 pictures. One of those has the power provided to it, and it forces the other one to move with it. So we talk about the driver and the driven, the master and the slave, if you will. And the driver is the one with the power, and the driver, the things we're going to look at to measure it, we might be talking about the diameter if we're talking about the drums, and we'll use caps for the driver and we'll use lowercase for the driven. And the driver might go through a certain number of revolutions, and the driven might go through a certain number of revolutions as a result. And these two terms should be equal. So if you remember our original drum, it had a circumference, a small circumference, and if n was 2, if it went around twice, and then you go to the driven, it had a bigger circumference, it was double, but it only ran around once, and this equation would perfectly hold. Okay, and this is the basic equation, and we're going to take this and change it for gears. We are going, because gears have teeth, we don't want to talk about diameter of a gear. We want to talk about the teeth. And so let's stop and come back. So we have a pen. So the letter for teeth is T, and big T and little t. Okay, so, and N is number of revolutions, but it could also be RPM. You're going to see the problems doing it both ways, and it's the same formula. It doesn't matter. If it's RPM, they both have the minutes in them, so you're getting the number of revolutions anyway. So this is our main formula. Yeah, and so when we're analyzing gear setups, and there's going to be more than 2 gears, we have to analyze who's the driver and who's the driven. And that's pretty easy to do. We'll look at pictures mainly to learn that. So let's go back to the slides. And here's, we usually, we're going to go left to right. So A is the driver and B is the driven. And there's a shaft in each of them. And so A is going to drive B. And as whatever direction A is turning, B is going to have to turn the opposite way. Because let's say the gear teeth of A in this picture, where it meets with, where A meets with B, the gear teeth of A, let's say they're going up. A is rotating counterclockwise. It's going to force the gear teeth of B to go up, and B will be rotating clockwise. So it'll be rotating the opposite direction. What if you have a third gear in there? Now let's call that gear M for middle. You have A and you have M and you have B. A is the driver. Who is the driven? Well, A is not touching B, so B cannot be called the driven. For A is only touching M. So that little gear in the middle is M. It is driven by A. Now, let's forget about A. B is the last one in the line. B has got to be a driven gear. Who is the driver for B? It's got to be the little one in the middle, M. So M wears both hats. M is a driver and M is a driven. And that's going to be significant for our analysis of gear trains. And we have 3 gears here. You can have more than 3. And that's where life is going to get a little interesting. So how many drivers are there in this picture? There's A and there's M. Those 2 are both drivers. How many driven gears are there? Well, there's 2 also. There's M and there's B. So M is playing both roles, driver and driven. And they call a gear like this that's simply filling in space to link these 2 together. This is an idler. Makes it sound like it has, no useful function, but it plays a very useful function here. It's transmitting rotational motion from A across to B. And the number of teeth are going to determine, for whatever speed A is rotating, that'll determine what B is going to rotate. Okay, so let's see what are we going to do here. Let's take our formula. Let's go back and look at an example. We've got a couple of examples, a lot of examples in this section 9.6. And then that'll wrap it up here. So let's go back to the whiteboard. And let's do a problem. That's the only formula we're going to use. It can be expanded a little bit. So example 1, a driver gear has 30 teeth. Okay, so I'm just going to put 30 here. That's the driver, has 30 teeth. How many revolutions does the driven gear with 20 teeth? And so they're asking how many revolutions is this one. So we don't know. That's going to be the thing we solve for. While the driver makes 1 revolution. Okay, easy problem. 30 times 1 is 30 divided by 20. N is going to be 1.5 revolutions. How many sig digs do we have here in this problem? Well, the driver has 30 teeth. Does that mean we have 2 sig digs? Is that a rounded off number? Maybe the driver has 29.7 teeth and we round it up to 30. Maybe it's got 30.4 teeth and we round it down to 30. No, this is an exact number. Teeth come in whole numbers. You don't have fractional teeth. If you ever see a gear like that, they don't exist. So you got to have whole numbers for the teeth. So those are exact numbers. So they don't count for the sig dig thing. And it said the driver makes 1 revolution. So it sounds to me like 1 revolution is exact. They're not talking about 0.95 revolutions. They're saying 1 revolution. That's an exact number. So I don't have any input. I have 3 numbers and they're all exact. So what do? Well, you take the answer you get out of your calculator and use it. So 1.5 is the proper answer here. And we would box that one. And so here's a problem where sig digs are just totally irrelevant because you don't have any. All right, so now let's look at example 2. A driven gear. Let's erase a bunch of stuff. We'll keep the formula, but we'll get rid of all the stuff we did here. And we want to go out and back. And example 2, a driven gear of 70 teeth. So we've got 70, makes 63.0 RPM. That looks like 3 sig digs to me. The driver gear makes 90.0 RPM. What's the number of teeth required for the driver gear? Okay. 70 times 63 divided by 90. The driver gear needs to have 49 teeth. And you got to put your units, and your units here are teeth. Okay, that's example 2. Pretty straightforward stuff, don't you think? Okay, now the next example 3 is not a computational example. It's we're learning how to tell which direction is everything moving. So let's go back to the pictures. Okay, well, let's talk about this picture. Let's say A is going counterclockwise. Can you see that because A goes counterclockwise, the teeth where A is meshing with M is going to cause M's teeth to go upwards in the picture, and that will give it a clockwise rotation. And when M articulates into B, the teeth are going down, and they're going to push B's teeth down, and B will go counterclockwise. So A and B will both be going counterclockwise. And M in the middle will be going clockwise. It's kind of a general principle, you might think, that if we had a 4th gear, which would be a 2nd M, and a 5th gear, which we might call C, that A, B, and C, the 1st, the 3rd, and the 5th, would be going counterclockwise. And those in the number 2 and the 4 position would be going clockwise. So you might come up with a rule to say that the odd-numbered ones are all moving in the same direction, and the even-numbered ones are moving all in the same direction, but opposite to the odd-numbered ones. That works sometimes, not always. So let's go to the next slide. And Oh, these are the examples. So we just did the one with 30 and 20, and we did the one with 90. Okay, now we're into example 3, and there's 4 pictures to look at here. Here are 2 gears that are meshing. There's 2 rods, shafts that the gears are mounted on. As we're looking at A, it looks to us like it's going clockwise. So that causes B to have to go counterclockwise because of the action of the A teeth on the B teeth at the intersection. A teeth are going down, they force the B teeth to go down. So we have the driver and the driven. Here's an A and a B with a little M gear in the middle. And notice they're showing us that A is going clockwise and so is B. And it doesn't show what the M gear, the idler, is doing. It's going counterclockwise. And we have 3 shafts. So the shafts are also turning the same way the gears are. The gears are welded onto the shaft. And here we have, look closely at the B gear. There's 2 gears there that are on that shaft. We have 3 shafts, but we have 4 gears. And let's follow the motions of them. A is going clockwise, and the middle gear, M, has to be going counterclockwise. Now, who is the middle gear articulating with? It's articulating with the smaller B gear. Let's say the B gears are B1 and B2. B2 is the big one, B1 is the small one. And it looks like, at first glance, you think B1 has a lot of teeth, but it kind of looks like they match up with the number on B2 in this picture. But the M gear is making the B1 gear move, and the B2 gear is welded onto it, so it has to do the same thing. So A is pushing M down at its articulation, forcing M to go counterclockwise, and M is coming up where it meets the B gear, and it forces the B gears to go up, and they go, as a gear, the gear as a whole, it goes clockwise. And so we see the transfer there has worked. And now here's, we have 6 gears and 4 shafts. What's going on with this? Who's articulating to whom? And let's give names to these. One of our names is, we have A, and then we have M, but there's a little m is M1, and big M is M2. That's on the second shaft. And then we have the third shaft with a single gear. Let's call that N. And then we have the B shaft and 2 gears. We have B1 and B2. So A is articulating with M1, and M2 is articulating with N, and N is articulating with B1. So what direction are things going? A is going clockwise, so that will force M1 to go counterclockwise, which makes M2 go counterclockwise, and that's going to make N go clockwise. And if N goes clockwise, articulating to B1, B1 has to go counterclockwise, and so does B2. And that matches with the arrows that we're seeing. So if we are counting gears here, we have 1, 2, 3, 4, 5. The 5th gear is B1, and the first gear is A. B1, we said, is going counterclockwise, but A is clockwise. And the rule we had with the odd-numbered gears going in the same direction is violated. So that's not a good rule. A better rule would be to think about the shafts. If the first shaft is going clockwise, the second shaft has to go counter, and the third shaft has to go clockwise, and the fourth shaft has to go counterclockwise. And that would be a good rule for us. And let me see, there was one other thing. Was there one other idea here? We talked about the motion, we've talked about the gears meshing, the teeth. Oh yeah, how many drivers are there in this picture as you're looking at them? Who's a driver? A is a driver. A is driving M1. Is M1 driving anything? Nope. But M2 is a driver, it's driving N. Is N a driver? Yes, it's driving B1. So we have three drivers here. We have A, we have M2, and we have N. Okay, how many drivens do we have? Well, B2 is driven, and B1 is driven, N is driven, and M1 is driven. That's 4. But wait a minute, what about, is B2 really driven? B2 is on the same shaft as B1. B1 is the only one that's really driven. B2 just goes along for the ride. So I only have 3 drivens. I have M1, I have N, and I have B1. I should have the same number of drivers as driven. I think that's a fair rule to say. Okay, so let's see. I think we have pictures for the next bunch of problems. So let's go to the next picture. And this picture is on page 254. And we have 4 gears. We have 3 shafts. We have A with 30 teeth. We have B with 45 teeth. We have C with 15 teeth. B and C share the same shaft. And we have D with 60 teeth. Now, let's read the problem, see who is the driver. Find the number of revolutions per minute of gear D if gear A rotates at 20 RPM. Okay, so A is the driver, so B is driven. C is not driven, but C is a driver. So 2 drivers here, A and C, and 2 drivens, B and D. Okay, let's go back to our formula. So our formula only has 1 driver, 1 driven. So we have to see if we make a good change to that so it'll work for everything. Let's go back here. So here we are. And let's get rid of the last exercise we did here. So see if we can take all this out easily. All right, that was the formula we had at the start. And I want to move that equal sign. So now let's just hop out, hop back. I'm going to put that equal sign over here. So if I have more than 1 driver, I'm going to have to number them. And let's just see. I'm going to have to change that formula because now it's the teeth that are, N is the number of revs or the RPMs for the driver. And if there's a lot of drivers, they all have different teeth. But we're not interested in these problems in what is the RPMs for each and every gear. We're just interested in the one at the beginning, the one at the end. Okay, so I need my pen back. So let's get our pen back. And so Our driver is going to have an RPM and our driven is going to have an RPM. And the first gear for the driver is going to have teeth, and call that T1. Then maybe there's another driver as you're going along, and you're going to have to count the teeth there. It's T2. And maybe there's a third driver, and you could have a T3. And dot, 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 you got to put in a number for each and every driver that there is. If you got 5 that you can identify as drivers, you put in 5 teeth numbers. And that same idea happens over here. So for the driven, the first working from left to right, we count the number of teeth on each one. And this particular problem, we've only got 2 drivers and 2 driven, so we don't need to go past T2s. And in this problem, A and C were the drivers, B and D were the drivens. And the problem says, find the number of revolutions of gear D. Okay, so that we want little n. If gear A rotates at 20.0 RPM, 3 sig digs here. This is the only number that matters, because everything else is an exact number. A and C are drivers, and the teeth were 30 and 15. So I'm not going to flip back and forth with the pictures. 30 and 15 were the teeth for A and C respectively. We don't know what the driven RPM is. We're going to find that out. And then we had 45 teeth on B, and we had 60 teeth on, that's a dot, 60 teeth on D. And there's our equation. So let's divide both sides by 45 times 60. So that leaves there, and this comes in over here. And this is a quick calculation to be able to do. This does not have to be a whole number, because it's the RPMs. The teeth have to be whole numbers. And so when you compute this, you're going to get, and you need 3 sig digs, you're going to say 3.33 RPM. And that's how we do this kind of problem. Okay, let's jump out, see what the next problem is going to be. Back to our pictures here, go to the next one. And this is example 5. Looks kind of similar, but I think we have different numbers. We have 1600 RPM we didn't have before. Who are the drivers? Looks like A and C. Who are the driven? It's B and D. And it looks like I just have to change numbers in our, when I go back. What do we got to find out here? Find the RPM of gear D. This is the same problem. They just changed numbers on me. So let's hop back. Hello, whiteboard. Come on, there you go. Okay, so A and C are still the drivers, B and D are the drivens. I'm going to have to erase. I'm just going to have to erase the calculations we did here. Okay, out and back. All right, so now let's, the data we're given, we're told the driver is going at 1600 with the dash over the first 0, so it's 3 sig digs. The drivers are the A and the C. We had 60 and 15. we want to find the little guy's RPM, so that's N, and the little guy's teeth were 30 and 48. Pretty simple mathematics. You can multiply these things out and then divide one by the other, and I'll just go straight to the result. And this comes out to be 1,000 RPM. Okay. Let's look at one that's a little more complex to think about. So back to the pictures. Here's our next example, 6. We have, how many gears? We have 5 gears here, we have 4 shafts. And A is the driver, and E is the driven at the end, and we have a chain of them in between. So A is a driver who drives B. B is a driver who drives C. D has to be a driver driving E. But D is not driven because there's no gear meshing in its teeth to drive it, only E, which is driven. So the drivers are A, B, and D. And we have the little n. We have to figure out what is the big N, I think, in this problem. Yes. Okay, so back to whiteboard. And what did we say? We have A, B, and D. We have a little erasing here. A, B, and D. Okay, so these change. And all the rest of this stuff. We can take this out. So, out and back. So A, B, and D are the drivers. C and E are the drivens. Okay, now all the data is in that picture, and the picture is on page 254. So little n is 225 RPM. And then C and E. C has 10 teeth, E has 12. 10 times 12. Okay, and we want to find out what is big N. And the drivers are A, B, and D, so the teeth are 20, 45, and 30. Okay, so we divide. Divide all these numbers out and put them over here. So we have 20 and 45 and 30. And then you run the numbers to get the RPM. So N is going to end up being 45 RPM. And let me see. Wait, we're missing something here. We should have the same number of drivers and driven, shouldn't we? So let's go back to that picture and see if we spot an error. this is a good error to catch. So let's go back and see. How many drivers do we have? We have A and B and D. Very good, we got that. How many drivens do we have? Aha, B is driven, and so is C and E. So we missed B as a driven. Let's go back, fix that. Easy to fix. We're going to put in B here, and B is 45, so let's tack it on here. What you want to see in this is that 45 is showing up in the numerator and the denominator. B is a driver and it's driven. B is an idler. B wears 2 hats in this gear train. And because of that, B doesn't count in the calculations. B cancels itself out. So right away, that's the first thing you see when you have that, and you write these out. So you can cross them out and put the rest into your calculator. And 10 and 20 give you a 1/2. 12 and 30, they don't do it quite that. It's going to be 2/5. So it's going to be 2/10. What are we getting on this problem? 45 RPM. Does that look about right? Yeah, 2/10. So divide that, you get 22.5 times 2 is 45. So that's correct. And your calculator will do that without all the mental stuff. So we've got that figured out. And that is the last example here, I think, that we're looking at. So let's go back to the slideshow and see if that slideshow is, as it were, over. So we stop the share and we go into the slides. Let's see. Here we are. Okay, so hit the next one. Yeah, slideshow is over. So we have just completed our session. And we will continue with chapter 12 is our next chapter, and 12 and 13 for the rest of the week. So terminate the share, and we're going to end the meeting now. So I'm going to stop the recording and say bye.